Okay, good. So, welcome. Good afternoon, /evening. So today, as promised, we're wrapping up our electrostatics. Also, you should have been able to submit your homework solutions. And for the record, of course, I will post the solutions, but I usually write those and make modifications based on what I see are things that my students are bumping into. Issues tend to vary a little bit, so yeah, we'll do that after. But yes, you should have a solution set for that. Okay, so where did we leave things last time? So we started with a we actually finished the uniqueness of the curl divergence decomposition of the electrostatic field. Now I want to make something really clear. Just like there are in E&M, there are 20,000 different right-hand rules that are probably all related somehow. There's also a similar thing with the uniqueness theorem. There are many different uniqueness theorems. So we have to be really specific with what exactly we are talking about. So for instance, so if we have a vector field and we specify the curl and we specify the divergence, this particular version of the uniqueness theorem says that that curl and that divergence uniquely specify the vector field that you take the curl and the divergence off. It does not say that you cannot make changes to the curl and divergence and still get the same vector field. Because in fact, that's one of the things that we will run into later, where we actually have a gauge freedom, right? So we can, if we have a magnetic field, we can add a vector potential and we can transform the vector potential and the scalar potential and still end up with the same underlying physical field. So we're not saying that we can go backwards and say it's unique, because there is actually some freedom. All we're saying is that that vector field, once you have the divergence and the curl, that uniquely defines that vector field. So that's what we did. We did not say anything about the reverse operation because that's not specified. Okay, so that's the uniqueness, or one of the many uniqueness theorems. And of course today we will do the inversion, and we will show that doing some Fourier kung fu that you can actually invert these equations and come up with a description for that for that field. So we'll do that today, and then afterwards we have a couple of specific techniques that we need to go over. This is like I said before, this sometimes tends to become a course in differential equations, and I try to stay away from that as far as I can, but unfortunately it cannot be avoided. There are several cases where instead of solving the differential equation, let's say the Poisson equation, you wouldn't do it that way. You would just say, okay, I have some specific charge configuration, and rather than solving the differential equation directly, I use a high degree of symmetry and using integral forms of Maxwell's equations to figure out what the fields look like, because it's way faster than solving the differential equation in some weird geometry. But sometimes it cannot be helped, and sometimes you have to do that. There are also other situations where, for instance, you have a set of monopoles, for instance, just charged objects, and you want to know the field due to that. You would not necessarily solve Poisson's equation for a sum of delta functions, because that's needlessly complicated. You would just say, okay, I want to know the position, the potential at some point. You just take, okay, potential due to this charge, potential due to that charge, potential due to that charge. And then just take the sum and make sure you measure all those distances correctly. But that doesn't always work. So today we'll go over one example where that specifically doesn't work, and then how you do solve that. And I'll take a slightly different approach than the book, but we'll end up with pretty much the same closed expression. And in the end, as many of these things, you just have to take a Fourier transform and a convolution, and then you're done. So so that's that part. And then finally, there are very interesting limiting cases where you would want to know, for instance, what the potential is due to a charge distribution but you're far away from the charge distribution such that, let's say you have 1,000 point charged objects and you're far away, and you may not actually necessarily be able to tell all these objects apart, but you may be able to tell that, one part is slightly more positively charged than the other. So it looks a little bit like a dipole. And then if you zoom in, you might see, one side is a little bit more, there's a plus here, minus here, minus here. It looks a bit like a quadrupole. So, so then depending on how much you can tell about the interior details of that cloud of charges, you might start looking at the monopole, dipole, quadrupole expansion coefficients as you have more detail about that charge configuration. Now that's a that approximation is a well-known approximation. It's called the multipole expansion, and I'll walk you through how that's set up and try to give you a geometrical insight into why it has the shape that it does. Okay, so then finally we will, and we'll do that right after we invert that uniqueness section. We also need to talk about where the potential energy is stored in the field. Now, so if we have an electric field and we have an expression for the potential energy associated with an assembly of a bunch of point charges, right? And what we did, and we did this, was it last week, I think? We just said, well, we sum over the pairs. That sometimes is not a useful operation. So sometimes it's useful to actually write it instead of a sum over pairs as a sum of an integral of some kind of a source term and a potential term. But I mentioned before that sometimes when you do that, you start introducing weird things. So for instance, the double counting, which is why oftentimes you need to put a 1/2 there, and also the interaction of charged objects with themselves. Now, that is if you write your potential energy as just a sum of point charges that have associated pair energies with them, it's not ambiguous, right? You don't have to worry about charges interacting with themselves. But once you write it as a continuum integral over the entire field, you need to start worrying about all the singularities that are there. And we usually kind of throw that around, throw it away because it's so nice to talk about, to just have a description of what the potential energy of a certain field looks like. But I want you to remember that sometimes writing it in that manner introduces artifacts that are not necessarily supposed to be there. All right. So so last time we were working on that on that uniqueness section, and we said, okay, let's try to see if we can invert it. And inverting it, let's talk about what we mean by that. Okay, so okay, so we said that we have a some kind of a vector field, right? And U, and it's sorry, V. See, already begins V, and we have specified the divergence, and that's this scalar field f of r, and we also have specified the curl, and that is that vector field W of R. Okay, and we already said that this F and this W, they uniquely determine V. Okay, so they uniquely determine V. So we already showed that it is that is true, right? And now let's see if we can invert this relation. So so the first thing we'll do is we'll take the Fourier transform of this this equation. So we'll take the Fourier transform of the divergence, and then that should be equal to the Fourier transform of that F. Now, taking the Fourier transform of the Nabla operator is the same as pulling the Nabla operator out and then leaving this as an I and a k vector dotted with the Fourier transform of that field f of v. And now the Fourier transform of this f, we can call this, let's call it f of sub k. So this is the Fourier transform of f. The book uses a subscript k for the Fourier transform. I usually use tildes over it, but we also need tildes for other things. Unfortunately, that is not always helpful. But then we can reshuffle this a little bit, and we can just write this as a k dotted with our v, and now this is our our Fourier transform of that field v, and then we make our I go to the other side, so that's minus I, and now this is our f of k, and this is that k is a vector. All right. So so we've done this part. Now let's take the let's do the same thing with this one. So we'll take the Fourier transform of this entire thing. So we do the same thing. We pull out the Nabla operator. We get a minus I k vector crossed with, in this case, now the Fourier transform of v. It's that same object. And now the Fourier transform of w, we also call it w of k. Okay, so didn't really do anything. We just took the transforms. Okay, now let's see if we can figure out a way to get these two things to come together a little bit. So so we have a let me see if I have this right. Yeah, okay, so that minus is supposed to be here. Okay, plus. Yeah, it's an ik, not a minus ik. Okay. So let's remember here on the side. See if I can use a different color to make this a little bit stand out a little bit. So remember that we have this vector identity for a triple cross product. So if we take the cross of A and B, and then we say that is A dot C, that's a dot product scalar that we multiply with that vector B, then minus A dot B, and then that's a scalar again, and we multiply that by C. Okay, so that's our thing on the side. So let's see what happens if we take this expression and cross that with K. So I'll move the I over to the other side, so that's a minus I here, and I'll delete this here. So we will get a K crossed with, and then the parentheses are important, VK. Now I'm at some point I'm going to drop the tildes, but okay. So that is, according to this identity, supposed to be equal to A dot C. That's K dotted with V multiplied by that original field B, and B is the second here. That's K vector minus. All right, here we go. Now that A dot B, that's supposed to be K dot K. K dot K. So that's K dot K, and then multiply that by our V. All right. So that's our V. Now, of course, this is 1. And this we already had, because we had the dot product here of K and V. It is minus I times the F of K. Okay, so we have that now. And of course, the k dotted, the k crossed with this v also simultaneously is equal to this w. Okay, so now we have here k crossed with w. Okay. And now here we have equal to this. Yeah. That's a minus I. And this is a minus I f of k times k vector minus v. Okay. Okay. So if you now simplify this, you can pull out your v of k. That's your field that you're trying to solve for. And now you have just I, k with w, k minus k f, also of k, divided by k squared. Sorry, this is not 1, this is k squared, of course. Okay, so now we have, in a way, inverted our relation, right? Because that's the field that we want to know the solution for, and the only inputs are this w, which is that curl of the field, and the other is that f, which is the divergence of that field, right? So this is already the description that we needed for v of k. Of course, this is now still the this is still a Fourier transform. So if we really want to do this properly, we should do the inverse transform. So take the inverse transform. Let's see if I'm going to write that. So we'll do the inverse transform f minus 1 of v k. Okay, that's the inverse transform of, okay, here we go. So that's k with w over k squared. There's an I here somewhere. Ah, yes, there's an I of k. Yes, and then minus the inverse transform of k with the f of k, that's the scalar field, also with an I. Okay, now I'm writing this a little bit sloppy because what we want to do is, so we have this I of k, we're going to take the inverse transform, and we know that when we take the transform, we can always exchange an I times k for a Nabla operator. So this is written a little bit sloppy, but if you write it like this, then everything is good. So this is now the curl of the inverse transform of that w over k squared minus the gradient of the inverse transform of f. All right. Now the inverse transform here, I hope you see, is actually, it's a product of two terms, right? There's this w of k, and there's a 1 over k squared. And also here, this inverse transform is a product of two functions. So we know in the end, we will end up with a convolution. So we will end up with a curl of the convolution of, let's see if I can write this, if you can write this properly. Yeah, that becomes a little hard to write. Hang on a second. I was trying to take a shortcut. Okay, so let me see. So that's now this is over here is the original, right? Because we take the inverse transform of the transform. So this is our V. That's the original field V. And this is the curl of that field. So this, therefore, is this W. That's our W. And this is our F, the original F. Okay, so all we need to do now is to basically invert these two. What you then need is you need the inverse Fourier transform of 1 over k squared. And we wrote that down earlier. Let me see where we are. Yeah, we did that at the end of class. So then in the end, you get a convolution integral, which looks a little bit messy, but you get a convolution integral for this one, which is going to be that F d3x prime over okay, so that's our first one. And then this one is our U. That's 1 over 4 pi. Also W. Oops, that's an absolute sign. D3x. Okay. So in this calculation, we needed only a couple of things. We needed this cross product rule. We needed to remember that an IK becomes exchanged with a Nabla operator, depending on whether you bring it outside or inside of your Fourier transform. And also, again, our favorite part of also the entire reason of why we use Fourier transforms here is that you can always write the Fourier transform of the product of two functions as the convolution of the Fourier transformed functions themselves. So that's how we're able to invert this. So those were the hard parts, the tricky parts about this particular solution. So finally, it's minus the sorry, not divergence, gradient of this plus the curl of that W that came, oops, not W, U. That came out of this inverse transform. Okay, now let's talk about one such situation. So let's say given a some kind of a row. Oops. How do we calculate the potential? Now, let's say let's first try to determine our strategy. So let's say we have a some kind of a configuration of dots, and we want to know our phi here. How do we get it? Well, the easiest way to do it, if you're solving this problem, is use the superposition principle, right? Because you know that the phi of one charged object is let me see, it's Q over R. So all you do is, you want to know the potential there, you just take the sum of this, and this, weighted by all of their positions, and then you get the you get the potential. Now, this does not always work. So let me walk you through one example where that doesn't actually work. So, for instance, if we have a set of and this is a problem that is in the book. So let's say we have a set of lines here. These are charged lines. So they have linear charge density lambda. They're separated by a distance a, and that is in the x direction. So this is the x direction, and they're infinitely long in the z direction, and then the y direction is perpendicular to that, right? So these wires, they're lying in that xz plane, and now we want to know what is the potential here, somewhere at some arbitrary position. Now we could, let's say, take this wire and then basically write it as an infinite set of point charges, but you probably already know what the electric field is, and the electric field of a linear charge actually is so E of a cylindrical or linear charged objects goes like 1/r. Okay, now that immediately shows what the problem is with this approach, because that means that if you want to write the potential, you have to write the potential, it becomes the log. And then you've got divergences everywhere, right? So that doesn't really work very well, writing this as a sum of contributions from individual wires, because you've got logs here. And usually we get around the logs by putting a reference. So for instance, if we have the E field of a linear charged object, we give it some finite thickness, and we say, okay, use the potential at its surface as the starting point. And then you don't have the problem with putting r at infinity as the reference, because the log of infinity is still infinity. So you can't use an infinite potential as a reference. Can't do that here because these wires are infinitely thin. So we do need to figure out a way to invert the Poisson equation. Okay, so the Poisson equation. So the minus 4 pi rho. So we have to figure out a way to solve this. Well, the first thing we need to do, and we already went through this exercise a little bit, is how do we describe the charge density of a set of wires like this? So it's an infinite set of wires, and they're in the in the z direction and in the xz plane. So they are, they have a linear charge density lambda. They are located in that plane, so that means we need a delta function of y because they're in that plane at y is equal to 0. We also need a set of delta functions that will tell us exactly where they are. So this is going to be x minus n times a, and we basically let n, the index, run from minus infinity to infinity, or minus infinity to infinity. So that's our rho. I believe I didn't miss any terms. Yeah, I don't think we missed any terms. So given this rho, how do you find the potential phi? Okay, so this is where the Fourier transform is super useful. So we'll take the Fourier transform of this thing. equals to the Fourier transform of this, and then we invert it. So here we go. Taking the Napa operator twice, you get a minus k squared out. Okay, so we get minus k squared, and now we have the potential, but it's the Fourier transform, equals minus 4 pi rho, and that's the Fourier transform. Okay, now you can see this is this k squared that we also encountered when we were running into when we were trying to invert the field just a couple of minutes ago. So let's say we have this Fourier transform, we still need to get that phi by basically figuring out how that is convolved with a 1 over k squared, but we'll get to that in a little bit. But first, let's figure out what this Fourier transform is. So the Fourier transform is the 1, 2, 3. I'm doing 3 integrals, even though we don't really need the z component, but you'll see that it ends up not mattering. We could do this as a 2D problem or a 3D problem. So we'll take the Fourier transform and we'll take e to the power minus I k dot r, and now we need to actually transform this thing, so that's lambda delta y sum delta x minus NA. Yeah, and integrating that over all of the coordinates. Okay, so that's the Fourier transform that we got to figure out. The first is that the first thing we should notice is that we don't really have a z component. So that means that when we do our integral over z, we end up actually with 2 pi k z. And don't worry about that too much. If we started this as a 2D problem, we would have not worried about this. Okay. Now our delta y, our delta function for y. Where's my delta function for y? Yes. So our delta function for y means that when we take the Fourier transform, so that integral over dx, dz, dy, just picks up a factor 1, right? Because this thing at y is equal to 0 is just 1. So the y part of the Fourier transform vanishes. The z part gives you the delta function. And now the only thing we're left with is the x part of the Fourier transform. So that's our integral delta x a minus I k x x dx. All right. So this looks a little tricky, but really what you're supposed to note is that this is just a sum of n integrals, right? We're looping over n, and anytime you have a specific value of n, you are integrating from minus infinity to infinity over x. And the only thing that you're integrating is this thing. So for every one of those integrals, you will pick up a term where you replace the x by the NA. So you end up with a lambda 2 pi delta, and that's our kz still. And we'll end up with a sum over n still, but now replacing every x with an NA. Now it's not an integral anymore. So that's our Fourier transform for the charge charge density. And now we can go back and find the potential. So we know that the moving these over to one side, we know that our potential is going to be the inverse transform of this charge distribution times 4 pi divided by k squared. Okay, so I'm going to try to write this in one go. It's going to be quite long, but it's going to be 1, 2, 3 integrals. Our charge distribution, which is lambda 2 pi delta k z, and then there's a sum e to the power minus I kx and a. Now we also need a 4 pi, so let's stick a 4 pi in here. And then the actual inverse transform. So there's an I k r. Now divided by k squared. Now k squared, of course, is k squared x plus k squared y plus k squared z. And the inverse transform also is has this 1/2 pi cubed. Okay, now first thing I want you to know is that remember I told you it didn't really matter whether we did this as a 2D problem or a 3D problem, and now you hopefully see why. So the 3D problem was really only introducing a variable z that gave us that delta function, and now we're doing the inverse transform. That 2 pi and that delta function takes 2 pi out here, and it replaces anything here that has a kz by 0. And now you are left with a 2D Fourier transform that only mentions kx squared and ky squared, and you don't need to worry about the z component anymore. So it's nice to know that things still work out even if you don't take that shortcut. So that means that that term disappears. So we have only a lambda, and then there's a 4 pi over 2 pi squared. So let me see, that becomes times 2 over 2 pi squared. And then it's 2 integrals and still a sum over n. And now we have our e to the power I kx, and that's x minus na plus I k y kx squared ky squared dkx dky. So that is our potential. So this is essentially the integral that you'll find in the book, and then afterwards, the book actually does it a little bit differently. They actually they don't really do this with a straight up Fourier transform in 3D. They actually start by writing phi as a sum of Fourier components in X space already. So that part is kind of buried, but there is actually an X integral that looks just like this Fourier transform. And the rest is executing this integral, which again you do with contour integration. And again, that's where I draw the line. I say like, that's enough already. But that's the expression. That's how you would solve this problem. Now, this is, even though it looks a little bit tricky, this is really the best way to solve this problem because of this divergence of the 1 over r of the not this one, the log r of the potential. So that's why you cannot just do it by the superposition principle, and you need to explicitly do this inverse. So I hope you have some idea of how this whole thing goes, but the approach is still the same way. Take the Fourier transform, throw all your Laplace out, pick up k squared, k's and i's, and then throw in all your delta functions, and then in the end you'll end up with the inverse. So we've done this now. We've got 2 ways to find the exact solution for the potential as a function of position. One where we just use the linearity of the Poisson equation to just say, like, just write the sum of the potential as a sum of potentials to the point charges, or you can do this through solving the Poisson equation directly, and then sometimes you run into weird things with delta functions, but it is a straightforward process. You just need to do a really good job of bookkeeping and keeping track of where all the delta functions are. And of course, the other way to do this is to, if you have super high degree of symmetry, is to just use the use Gauss's law in integral form and find the field that way, and then just get the potential by taking negative the line integral. All right. Now, let's say we have some kind of a charge configuration, and so we've got A charges, and now we really want to know what is the potential here as a function of position, where we are using the approximation that we are quite far away. Now, so these A charges, they all have some charge QA. So the exact solution for the potential is not that hard to write. It's just phi of r is the sum over all of my charges A with a Q of A over R vector minus R A. Very straightforward. Now, if we're really far away from this set of charges, then if we're really far away, then it is as if all of these charged objects are all close together on a single spot, and therefore the first approximation to that potential is just the sum of QA over R. All right, so if they're all together, let's say, you know, we got 1, 2, 3 positive, we got 2, 3, 4 negatives, and they're all together, we could say, well, this thing is has a net charge of, let's say, -1 if they're all positive, you know, by the same amount and negative by the same amount. Then this just looks like a monopole for far away with a net charge of whatever that sum of the charges is, but we don't have to weigh the contribution from you know, the fact that they're all at slightly different positions. So that's our first order approximation to the potential when we're far away. Okay, now the next contribution is a little bit harder to look at, but so for instance, let's say we have some RA here. Okay, so this is R and then RA. Yeah, so this is the actual distance R minus RA. And let's say that we measure R from the center, right? So this is R. Then what we can do is we can say, as a second approximation, we can say, well, we can project the difference in position on the vector that is joining the center of that charge configuration. And that means that, let's say, if this object is here, then we are literally shortening that distance r by however closer this thing is. If it is in this direction, then it doesn't really change the distance to first order. It changes the distance to second order. So the second order is that projection of that position. Let me see. So it's still a sum over a. So sum. Oops. And then it's the that charge and the position RA, but now dotted with the gradient of 1 over r. So gradient of 1 over r, and that product basically is a linear modification of the distance, right? So if RA is perpendicular to the gradient of 1 over r, right? So in other words, you go in this direction, then that doesn't really contribute to this term. Okay. Now this is the so this is the monopole term, and this is the so-called dipole term. Okay, and if you want to do a do more terms, you can do what is known as the multipole expansion. And then really what you need is you need to figure out a way to expand this r minus RA for small deviations. So then what you get is you get 1 over RA. So first you get that 1 over r, that's just, whatever is at the center, minus, oops, and then that RA projected on the gradient of 1 over r. And now you do the same thing, but now you don't look at the gradient, but you look at basically the Laplacian. So RA dotted with the gradient, but then squared, acting on that function 1 over r. And then because this is a Taylor expansion, you use a 2 factorial. So that gives you, this is the dipole, this is the quadrupole term, plus 1 over 3. You can kind of see the pattern already. Cubed. And then again, acting on that distance r. So really, that's all we're doing. We're just saying, we just pick all these points at slightly different distances RA, and then if they are close together with respect to the total distance, how far that cloud is, then we can just do this this multipole expansion. All right, so that is the multipole expansion. All right. Now, final thing. The energy in the field. So we had already written. We had gone from a sum over pairs to an integral of the charge distribution with the potential, and then we integrate that over all of space. So we've done that already. But what we did not do is we didn't really connect this to the actual field. So one way to do this is to say, well, we know that the Poisson equation says that this must hold, which means that we can just solve for rho and stick this into this expression. So now we get, that's minus 1/4 pi times a half. Okay, and now we have the potential and then again the potential, but now the one from the Poisson equation. Okay, now this is a this looks a little tricky, but it's not too hard to simplify this a little bit. So let's do this. Let's do this here. So let's take the divergence of the following term. Okay, now if this is the divergence of the following term, then we can write this as, you know, product rule, okay, plus, oops, there's not a square here, Napa squared of phi, right? So hopefully you see that phi, Napa squared of phi, phi, Napa squared of phi, that's this term here. Okay, therefore, we can rewrite this integral. We can write this as minus 1/8 pi. And then the integral of the divergence of this term integrated over the volume minus, and now we have to subtract this term, minus 1/8 pi, and this is the gradient phi dotted with itself, right? And again, we integrate this over all of space. Now this this looks a little, this term looks a little funky, but we can actually we can change this using Green's theorem, because this is the volume integral of the divergence. You can change that to surface integral. So that becomes a surface integral of phi d phi dotted with the normal. Okay, now we usually assume that things don't explode when we go to infinity. Now look very carefully. So phi, if you're far enough away, certainly if you look at the multipole expansion, the leading term goes like 1/r, right? So that leading term goes like 1/r, and then the gradient of that goes like 1/r squared, and the surface goes like r squared. So this entire thing, when r goes to infinity, becomes 0. So this thing becomes 0. Okay, so that means that our charge, our energy here is U, is really only given by this equation on the right-hand side. So that's our E. And then, oh, I forgot a minus and a minus. Sorry, I moved this over to the other side. Yes. No, not E. U. Okay, and of course the gradient of phi is E. So the energy is the potential of E squared integrated over the volume. What does that mean? Well, that means that the energy is stored in the field. So energy density is stored in the field. There are many situations where you hopefully have seen this already. So for instance, if you take you take some kind of parallel plate capacitor, charge this positively, charge this negatively, and you want to know how much energy is stored in the capacitor, you can express that as the energy that's stored in this region between the two capacitor plates, and you can work out what the energy density is, and it turns out to be, again, exactly this E squared. The other place where you might have seen this is when you studied electromagnetic waves. So that's example 1. So in example 2, the energy carried by waves, and we will revisit it. It's stored by in both the electric and the magnetic field component, but the flow of this energy from in the direction in which the wave is traveling, it's given by the fact that this energy is stored in both the electric and the magnetic field component. Now, we haven't done the energy in the magnetic field component of the electromagnetic wave yet, because frankly, we haven't done magnetism yet. But that's where you will revisit and see this again. Now, you have to be really careful with this thing, because and I mentioned this in the beginning, of course, that if this electric field is due to a bunch of point charges that are all located within that volume that you're integrating over, you have to know what are you going to do with all the divergences. And usually we will sidestep that. We'll say that we shouldn't be doing this if we have point charges here, because we don't quite know how to deal with the divergences. So if we have that, then we need to treat it specifically as potential energy formed by the sum of all the charge pairs. But in the absence of point charges, where we don't have those divergences, then this is safe to use, and this is actually a very neat description, because it doesn't really require us to do anything funky with those divergences. Okay, ladies and gentlemen, well, we did it. There was much rejoicing. We finally made it to chapter 2. So the end of chapter 2. So yeah, like I said, I'll try to find the right balance between not doing too much math, but also not swiping too much stuff under the rug, because it is important. Like for instance, later on, I think we might find that talking about fields radiated by accelerating charges might actually be more natural to discuss in a relativistic context, and that allows us to describe the subject a little bit more neatly, but also will save us some time. So hopefully we'll try to find enough shortcuts that'll allow us to get to where we want to go without skipping over important details. But yeah, unfortunately, sometimes these calculations become so baroque that it's kind of hard to lose track of what we were doing and also why we were doing it. But yeah, so this part should be very straightforward. We just did electrostatics. Next part is magnetostatics, and of course, magnetostatics. That means that we're going to get cross products everywhere. You thought we had a lot of cross products in this particular chapter. It's going to be way worse in the next one. So hold on to your hats. And then we'll see you on Thursday. And again, I'll I have office hours right now, so for those of you that have questions, we can discuss.